welcome yet again. I guess last lecture was actually chapter 4, not chapter 3, like I accidentally mentioned. The first lecture, lecture 1 is actually on chapter 3. The lecture in the class is on chapter 2, and this is on chapter 5. This is the last chapter for the first midterm. So the first midterm will cover chapters 2 through 5, which is the one I gave in class and didn't do on video, through this lecture. Our goal for this lecture is to understand Newton's third law. So basically the first test is on Newton's first law, second law, third law, and linear motions. Expect to have one short answer question from each of those. Objectives, we're going to understand how actions create opposite actions. We're going to examine applications of this law, and we're going to learn how to save Batman from the clutches of the evil Joker. Now for those who are wondering where the heck did that come from, because you are not in my class, the first day of class I posed them a problem for them to solve at the end of the first midterm, which is if you put Batman on ice with no friction, so you can't walk, how do you save Batman? And you're on a really ridiculously large lake, so Batman has to save himself. So how does Batman save himself? I guess he's got a radio, you can tell him what to do. So we're going to learn how to save Batman in this hideous law. So Newton's third law is the law of opposite reaction. The first law is the inertial law. Motions stay constant unless a force acts upon you. The second law is F equals ma. It is still written on the board. The third law states that for every action there's an equal and opposite reaction. It's a law that doesn't just apply to physics, but almost to almost psychology as well. So if I exert a force on something, it exerts an equal but opposite force back on me. Meaning opposite in direction. So if I push, if I'm swimming in a pool and I push on the wall pushes on me and I go flying in the opposite direction. The last lecture you saw me push on the skateboard, and the skateboard pushed me in the opposite direction. Or namely, the skateboard pushed me this way, and I pushed it that way a lot. In fact, it's still sitting over there. So I push the wall pushes back. In fact, you can see me physically move backwards as I push on the wall. So I apply, let's call this the west direction. It's actually the north direction. But if this was the west direction, I apply 1,000 newtons west. I get applied 1,000 newtons to the east. So in this case, I apply 1,000 north. I get 1,000 south pushed on me. Okay, so what does this mean? What are some applications of this? So, the last lecture, I pushed the skateboard pushed me. The forces were equal but opposite. But since our masses were different, the accelerations were greatly different. It went 20 miles an hour, I went 1 mile an hour. Oops. Luckily, I ran into a door, so I didn't put a hole in the wall. All right, opening a door. I go up to a door. I push the door. Usually the door opens. But let's examine the physics behind this. In fact, I want you to talk to your neighbor first about this. Or your cat. After all, it's his fault you're watching this in the first place. Or her. So what's going on? Let's think about this. Net force equals sum of all forces. I push on the door, let's say 1,000 newtons. Okay, not that strong. Let's say 300 newtons. 1,000 newtons is about 200 pounds. So, 200 newtons, I push the door, 200 newtons open, to try to open it. And let's say it's a 50 kilogram door. What is the acceleration of the door going to be? Never ignore the fact that it would actually rotate. Let's imagine it pushed linearly. Well, now let's apply Newton's third law. I apply 200 newtons to the door in the forward direction. It applies 200 newtons to me in the backwards direction. What is the net force on the door? I'll leave it to you to solve that problem. Do the math, you shouldn't need a calculator. If you came up with an answer of 0 newtons, I am sorry, but that's not the correct answer. But why? Why is that not the correct answer? Didn't I just say there's an equal and opposite force? There's 200 on the door and 200 backwards on me. Wouldn't those cancel each other out? But the answer is no. The reason being is that when you calculate a net force on an object, you can only add up the forces being applied to that object. Since the I for an I force, the Newton's third law force, is being applied to me, that only applies to the net force on me. It does not apply to the net force on the door. And I'm pointing that way because there's a door over there. I know you can't see it because the camera's pointing towards me and not away from me. But there's a door over there. Just take my word for it. All right, so, and particularly because I'm videotaping this in a room that the class doesn't meet in, a big lecture room. So the students, even in my physics minor class, probably have never been in this room, and they wouldn't know that there's a door over there. Okay, so weird stuff that goes on that you don't even think about. If there was a classroom here, I pointed at the door, the students look at the door, there's no, you can't because the videotape's this one. Okay. Digression, digress from the digression. Okay, so the door gets a 200 Newton net force this way. I get a 200 Newton net force that way. But we both have net force on us. Neither one is 0. So it opens that way. I get pushed back this way unless my legs push the ground, which gives me a frictional force forward, which can counteract that as I push. And in fact, usually when you push a door, you have to brace yourself so that the door pushing back on you doesn't make you go backwards. Because if you didn't, if you just did this, you would fall backwards. Like that. And so instead I would do this. Okay. So that answers this question. All right, so hopefully now we understand the concept of equal and opposite forces and how that applies to net forces on particular objects. All right, so how does walking work? So, when I walk, I push the ground this way. The ground, they're not happy with me for pushing it and pushing it this way, pushes me this way with an equal and opposite force. But luckily that was the direction I wanted to go anyways, and so I go that way. So this is all because of Newton's third law. We could not walk or drive cars or do pretty much anything without Newton's third law. Rockets. Yes, I'm going to teach you rocket science today. Well, the very basics of it. How do rockets work? Well, in a rocket you have a propellant inside the rocket. You expel the propellant downwards. That means that the rocket has to apply a force to the propellant to push it downwards, effectively. Because the rocket pushes the propellant out, the propellant then pushes the rocket up, equal and opposite force. So rocket science, rockets are all based on Newton's third law. If you want to test this at home, take a balloon, blow up the balloon, let the balloon go, the air gets pushed down, the balloon goes up. If you want to make it go up faster, you put water in the balloon, and about half water, half air. Then the mass of the water you push down is a lot, and so you get a lot of push up as well. Because more mass being pushed at the same acceleration means bigger force. So to recap, rocket exerts force on gas. Gas exerts equal and opposite force on rocket. Gas and rocket go in opposite directions, all because of Newton's third law. All right, recoil. Again, we're in Indiana. Indiana is a red state. We like our guns in the state. So, an example about guns and cannons. You take a gun. You shoot it. What happens? There's a recoil. The gun pushes back. Why? Because the gun pushes the bullet forwards. The bullet pushes the gun back. So you try to push the bullet into the target tries to push the gun into you. Cannon. You don't want to stand behind a cannon when it's shot, because the cannon will recoil as well. And it's a pretty big bowling ball, so that's a pretty big cannonball usually, so they have a lot of force, and so the cannon goes back into place. In fact, there was the old adage, a loose cannon. Well, if on board a ship, if your cannon wasn't tied down well enough and you shot the cannon off, the cannon could slide all the way across the ship and out through the other side of the ship. Not meaning through the porthole on the other side of the ship, meaning through the ship, leaving a big cannon-size hole in the ship, which would sink the ship. Oops. What about gravity, though? Is gravity the loophole to Newton's third law? Good thing about studying physics is you get to learn about the loopholes. Is this the loophole? Well, let's test it. I'm going to take an object, and I'm going to drop it. I dropped it. The Earth exerted a force downwards on the eraser. Now, by Newton's third law, there should be an equal and opposite force on the Earth. Did any of you out there in TV land suddenly see, or feel on the day that we did this experiment, this being the 18th of August, yeah, I'm doing this way in advance of this my spring semester. Did you feel the Earth go the other direction? Let's try it again. Did the Earth move? The answer is kind of. But you didn't see it, did you? It didn't appear. So what's going on here? Well, let's examine the equation. This is like our skateboard example all over again, except for at the extreme. Force equals mass times acceleration. Acceleration on this is 9.8. Its mass is a tenth of a kilogram. The Earth has a mass of 6 times 10 to the 26 kilograms, give or take. Yes, it's a number I haven't memorized. I'm an astrophysicist, go figure. So what's its acceleration? So 10 times 0.1 is 1 Newton. So we put that in for the force on the Earth. 1 Newton equals 6 times 10 to the 26 times acceleration. Acceleration equals 10 to the minus 25th, give or take a factor of 2. So it did accelerate, just not very much. Not enough for us to be able to see. So, no violation of Newton's third law. Sometimes you have to look at the bigger picture to see everything being encompassed. I think that covers that slide pretty well. So, let's do a quick question before I move on, because I haven't had any sample problems yet. I know how you students like their sample problems because we learn by doing. And it helps to do if I actually have a pen. Okay, we're going to have 2 people in space. So there's no gravity, no friction, nothing like that. We're going to have a big guy and a small guy. Big guy. Okay, this is probably me. And the smaller person. Okay. The big guy is going to push the small guy this way with a force of 300 newtons. The small guy is going to try to push this way with a force of 100 newtons. Here's what I want you to calculate. What is the net force on the small guy And what is the net force on the big guy? So go ahead and pause it at this point. Go ahead and do the calculation. Did you guys have this for something?
No, we have a class in here. We're just wanting to look.
Oh, okay.
So that's a lead, don't worry.
I'm going to do a recording for spring. All right. I think that's enough time. It'll be fun when you video record the week before class starts. Okay. Which is the only reason I have this room today. So, let's examine the smaller guy. Net force is the sum of all forces. So how many forces does this guy have on him? Well, clearly he has the 300 Newton force on him, going that way. Because the big guy's pushing the little guy directly. This is a direct force. Well, what else? Well, he's pushing this guy. And so as a result, he's going to get a force back from Newton's third law. So since he's pushing this way at 100 newtons, he's going to get a force this way at 100 newtons as well. Now these forces are both in the same direction, so that means his net force is going to be 400 newtons this way. And yes, please on test circle answers, it helps me greatly in the grading. All right, so what about the big guy? Well, we know the big guy's getting 100 newtons this way from the little guy. What else? Well, he's pushing him, but he's going to get a Newton's third law back. So he's going to get 300 newtons back from Newton's third law. So again, this is the from big, and this is the third law. This is from small, and this is the third law. And so the total is 400 newtons this way. Now notice in this case, the net forces on each person is equal and opposite. That's not a coincidence. Even if you took one of these forces away, let's say we take away this force. Well, then his force would just be 300, and his force would be 300 back the other way. Again, equal and opposite. Now let's turn to Batman. Suppose we put Batman in the middle of a lake. And this is a long lake. A lake so wide that you can't even see the shore. And it's made of a special ice created by the Joker. And this ice has a special property that has zero friction. None. And Robin's nowhere to be seen. You can assume that Batman has his normal tool belt. How does Batman get off the lake? He can't walk. He tries to walk, his foot slides. He goes nowhere. He can't crawl, because if he does this, his arms just slide and he goes nowhere. Normally, doing this would move in water, etc., because you have friction. There's no friction. So how does Batman get off the lake? Well, it turns out we need all of Newton's 3 laws to be able to solve this problem. In order to get him to move, we need to apply a net force. That's what Newton's first law states. The second law states that once we apply a force, the acceleration will be equal to mass, or the force will equal mass times the acceleration, we'll get the acceleration now. But how do we get the force in the first place? Well, it turns out we get that force from Newton's third law, which means that Batman has to exert a force on something that will give him an equal and opposite force in the opposite direction. So where could this come from? So brainstorm that for a minute. Go. And here are some possible answers. So, if he's got a gun, which Batman usually doesn't, he could shoot the gun. The recoil will push him back the other way. And then he could throw the gun. Throw the gun? If he throws the gun, he's applying a force to the gun. The gun is then going to apply a force to him in the opposite direction. Gun goes one way, he goes the opposite direction. He can shoot his grappling hook, but he has to be careful with the grappling hook because the grappling hook usually is on the line, and at the end of the line, it can pull and stop and pull back. So he'd have to cut the line before it hit the end. Or he can even take her shoes off and throw the shoe. Really, what superhero throws the shoe? And there's many other ways for him to get off. So to recap, Batman has to generate a force using Newton's third law. He has to apply a force on an object he has on him in order for that object to apply a force equal and opposite to him. That will give him an acceleration, F equals ma. It'll be a very small acceleration. He won't go very fast, but he will move. And then the first law, which gave him the motion in the first place, also protects him because now, since there's no friction, it will keep moving until force acts upon him, which will be him running into the shore. And so Newton's three laws will save Batman. What will not save you 15% on car insurance? I'm sorry, just all right, so to wrap up, any type of force is applied, an equal and opposite force is applied back, Newton's third law. This allows us to walk, this is the basis for rockets, and this even saves Batman from the frozen lake. All right, so that's all for today. I will see you in class where we will do some problems based on this. Some car hijinks may ensue.